Homework 13, the rational zero theorem, video 3. In the previous video, we were introduced to a theorem called the rational zero theorem, which gave us a way to manufacture a list of possible rational zeros. In other words, possible whole numbers or ratios of whole numbers that would make this function equal to 0. But how can we capitalize on that? Well, this goes back to our original task of finding the zeros of a function, sometimes in the context of finding x-intercepts of a graph. So how do we do this? Well, we need to find a number that will give us a good synthetic division problem. And by good synthetic division problem, I mean a remainder of 0. When a synthetic division problem has a remainder of 0, we have two factors. One based on what we divided by, and the second by the bottom row, which represents the quotient of the division problem. What you see here is pretty typical in the homework. Here's a function, list the possible rational zeros, use synthetic division to locate an actual 0, and then find the remaining zeros. So here's how it would go. First, we need to list the possible rational zeros. And remember that the rational zero theorem says that the only numbers you need to consider have a certain form. The numerator will be a factor of the constant term. So on the top, we need to write factor of 15. The denominator will be a factor of the leading coefficient. Oh no, I don't see it because it's the number 1, best leading coefficient to have. Because on the denominator, it has to be a factor of 1. And keep in mind that all of these will be of the plus-minus variety. So let's see what our factors are. Let's start with the denominator. The only whole number factor of 1 is 1. Yay, none of our fractions will actually be fractions because the only denominator is 1. But on the numerator, we need to list all the factors of 15. And again, you can grab them in pairs. For example, 1 factor of 15 is 1, its cofactor is 15, because 1 times 15 is 15. 15 is odd, so it's not divisible by 2, so 2 is not a factor. But 3 is, because 3 goes into 15 5 times. 4 isn't a factor, and by the time we get to 5, we're repeating ourselves, so this is the total list. The only fractions we can make are over 1s. I'm going to do something a little bit different in this list. I'm going to separate the positives and the negatives. So we can have 1 over 1, so that makes 1 and negative 1, don't forget plus minus. 15 over 1, so that makes 15 and negative 15. 3 over 1, so that makes 3 and negative 3. And then 5 over 1, which makes 5 and negative 5. So if this were a homework question, this would be the answer to the first problem. Some of the questions that ask you to list the possible rational zeros will be multiple choice, so you just have to pick the correct list. Some of them will ask you to type it out, so be prepared. And remember what that list is. The only whole numbers or fractions that can make this equal to 0 must be in that list. Which one is it? We don't know. But that's where step 2 comes in. We're going to use synthetic division to locate an actual 0. Another way to think about this list, instead of calling them possible rational zeros, which they are, is to call them potential box numbers in reference to synthetic division. All of them can be box numbers, but what we're looking for is a box number that gives a remainder of 0. Which one should you try? I don't know. So you try one. If it works, great. If it doesn't, throw it away and try another. For example, let's try the number 1, which will always be in your list as the box number in a synthetic division problem. The top row would be 1, negative 1, negative 1, 15. 1, negative 1, negative 1, 15. Here's why you need to be very proficient and efficient with synthetic division. This is a lot of trial and error, and you're going to have to go through a lot of synthetic divisions. Just remember, add the column, multiply by the box. 1 times 1 is 1. Add the column, hooray, we got 0. Oh, a little too early to celebrate. Multiply by the box number, 0 times 1 is 0. Add the column to get negative 1. multiply by the box number to get -1. And at this point, I can shut it down. I'll finish the division by adding the last column and getting a remainder of 14. But we're looking for a remainder of 0. The moment you know it's not going to be a remainder of 0, stop, throw it away, and in your list, cross out the number that failed. 1 down, 7 to go. I will tell you that there is only one number in this particular list that works. I invite you to pause the video and run them through synthetic division until you find the one that works. Hopefully you've paused the video and found the one number in the list of possible rational zeros, the potential box numbers, that gave us a remainder of 0. I know which one it is because I built this problem. The only number in that list that works is -3. So if we reset a synthetic division problem, 1, -1, -1, and 15 is the top row, I should get a remainder of 0 at the end. Add the first column to get 1, multiply by the box number, 1 times -3 is -3. Add the next column to get -4, multiply by the box number, -4 times -3, something's going awry here. I'm going to go ahead and push this through and try to figure out what happened, because this was supposed to work. -4 times -3, make sure I wrote everything down correctly. Oh, I didn't. Oh, shame on me. I even messed up here, but this still wouldn't have worked. My top row is incorrect, and you were probably screaming at me earlier in the video, you set it up wrong. Because the top row isn't 1, -1, -1, 15. The top row is 1, -1, -7, 15. So I can't let this one go. I'm going to have to go back and fix it, but that'll be minor. This was supposed to be a -7, which means the sum was supposed to be -7. Times 1 is still -7. The sum is 8. That's still not 0, so it's still not one of my not the number I want from the list. Now let's fix it here. It doesn't matter how good you are, it is easy to make careless mistakes, so focus and pay attention. Now it should work. Let's recap what happened. Add up the column to get 1 times -3 is -3. Add the column to get -4. -4 times -3 is 12. Add the column to get 5. -3 times 5 is -15. Hallelujah. Smiley face. Because I got a remainder of 0. That's what I wanted. Sometimes if you do many failed attempts at synthetic division, or rather failed attempts to locate a 0, and then you finally find one, you are smiling because you're like, it's about time. All right. So what does this tell us? Well, it tells us a few things. It tells us 2 factors of our function. Remember that one factor in the context of division is the divisor, which came from the factor of x plus 3. Remember, when you set up a synthetic division problem, you put the opposite, the opposite of the number in the divisor into the box. So if our box number was -3, and then our divisor was x plus 3. So if we put that equal to 0 and solve it, we get x equals -3. And from this, you can glean a quick but important observation. If a box number has a remainder of 0, then that box number is a 0 of the function. So when we were asked to locate an actual 0, we found one. -3 was an actual 0. You can check it by substituting it into the function, but it has to be because it's one of our factors. And if this factor is equal to 0, then the whole multiplication problem is equal to 0. So that's how you can locate an actual 0 of a polynomial function, by finding the box number that produces a remainder of 0, where your box number comes from your list of possible rational zeros. But what about finding the remaining zeros? Well, recall that what we are attempting to do is solve this equal to 0. X cubed minus x squared minus 7x plus 15 is equal to 0. And the general strategy is get it equal to 0, it already is, and factor it. if you have a division problem whose remainder is 0, one factor comes from the box number. So one factor was x plus 3. We already know what that's going to give us. But the other factor comes from the quotient, the bottom row of the synthetic division problem. Just remember to lower the degree by 1. This was a third-degree polynomial, so the quotient will be a second-degree polynomial. This represents 1x squared. The minus 4 represents minus 4x. And then the 5 at the end represents a constant of plus 5. So a good synthetic division problem with a remainder of 0 gives us 2 factors of our function. And again, we already know what this one does. When we put it equal to 0 and solve it, we get negative 3. In the homework, when it asks you to list all the zeros, I'm going to rephrase this. Find all the zeros. That includes the one that you already found in step 2. But now we got to find the zeros from this factor. And you could try to factor this, and I'll tell you right now it won't. The only way that you're going to solve x squared minus 4x plus 5, well, there's a couple of ways. One is completing the square, but we just kind of brush that under the rug. You could use the quadratic formula. I'm going to expedite it. The top is negative b. B is negative 4, so negative b is positive 4. Plus or minus, we'll get to the square root in a minute. The denominator is 2 times a. A is 1, so 2 times 1 is 2. Under the square root, we have b squared, so 16, minus 4 times 1 times 5, minus 20. So 16 minus 20 is negative 4. Here we go, the square root of negative 4 is 2i. So now we have 4 plus or minus 2i over 2. If we split this into 2 fractions and reduce them separately, 4 over 2 reduces to 2. And 2i over 2 just reduces to I. So all of our zeros are negative 3, 2 plus I, and 2 minus I. Those are the zeros of the function. Why were these two not listed up here? Because they're not rational zeros. They're not even real numbers, much less rational. If we were finding x-intercepts, the only one would be negative 3 because you can't find imaginary x-intercepts on a real number x-axis. So the general strategy for solving a polynomial function equal to 0 or finding the zeros of a polynomial function is to list the possible rational zeros by listing factors of the constant term over factors of the leading coefficient. Then get ready to do a lot of trial and error synthetic divisions by putting these numbers in as box numbers one at a time until you get a remainder of 0. When you get a remainder of 0, you found 2 factors. One of them comes from the box number, the other one comes from the quotient. Also remember that if a box number gives a remainder of 0, then that box number also doubles as one of your zeros of your function. There's no need to rebuild its factor. Then you can use the results of the synthetic division problem to factor the original function, but you really only need to focus on the factor from the quotient at the bottom, because the factor that came from the divisor, we already know it's 0. You may have to use the quadratic formula, and you may get answers that aren't rational numbers, but that's okay. All right, it's a lot to do, but we're going to take a look at another.